Hello friends, so today we are going to solve, or we can say we are going to continue with 3 questions, and these 3 questions are based on the, you can say, the conservation, energy conservation as well as the momentum conservation. And so in the first question, it states that a point particle of mass m is initially at rest at the top of a smooth rigid hemisphere of mass m. The hemisphere rests on a smooth horizontal table, so all the surfaces are frictionless. The particle is given an infinitesimal horizontal push and begins to slide down the surface of the hemisphere under gravity. At what angle of theta, measured from the vertical line through the top of the hemisphere, does the particle lose contact with the hemisphere? For the general case m is not equal to capital M, it is sufficient to derive the equation satisfied by theta. This equation will be cubic. We will see to that. And for the special case m is equal to m, solve the equation explicitly and determine the angle at which the separation occurs. So this question is pretty long, but if we try to understand in the simpler terms, we can just draw the figure. So we are having a hemisphere, and let us suppose this is the center of the hemisphere C, and we draw a vertical line, and initially the particle is at the top, r is the radius, and then it slide, you can say slight push is given to it, the particle, and let us suppose this is the position, and here it is making angle of theta. So if we can say that at this particular point v its is velocity, and we can, or let us say u is the velocity, and mg will be in the downward direction. So capital M is the mass of the hemisphere and small m is the mass of this particle. Okay, and we have to find out theta when it is going to leave this hemisphere. So obviously at this particular moment, let us suppose it starts from A and leave the hemisphere at point B. So at point B, the normal will be equal to 0. This is the basic, you can say, between whenever there is loss of contact, the contact force comes equal to 0. Okay. So, and so let us denote that the particle speed relative to the hemisphere is, let us suppose, given as u, and the horizontal speed of the hemisphere is, let us suppose, is given as capital V. Okay. Therefore we can write that absolute velocity of the particle, and let us denote this absolute velocity as V. So we can say the absolute velocity of the particle velocity of the particle, that is over v, will be equal to over u plus capital V. And this is over u, not v. Okay. And now we can divide our, you can say, the velocities into components. Okay. And for that we are going to get that this angle will be also over theta. So we are going to have two components. This will be u of x and this will be over u of y in the downward direction. Therefore we can write, and let us use the conservation in the horizontal momentum conservation. So you can say horizontal momentum conservation, and there is no net external force. Therefore we can write that our m v of x plus m times v should be equal to 0. And we know that our this horizontal velocity of the particle which is our v of x. So v of x will be equal to u cos of theta plus v. And so we substitute this v of x here and we get m times u cos of theta plus v plus mv is equal to 0. And from here we can easily calculate our value v will be equal to, this comes as our minus mu cos of theta and divided by m plus small m. Okay. And in this case we have to remember, because of the conservation of the momentum, because the velocity is only, or we can say the initial push is only applied to the particle, but because of conservation of the momentum, this hemisphere is also going to move because everything is frictionless. Okay, therefore we have said its velocity in the horizontal direction is our v. Okay. Now we come to our energy conservation. You can say energy conservation, and so in energy conservation, let us call this as initial energy, and denote it as E of I, and let us denote that our initially the particle was at position A at a height r. Okay. And so we can just, so initially this is center, this is position A, and this height is given as our r. So this is the initial position of the particle, and the final position of the particle is our point B, which is at angle theta. Therefore this, let us call this C prime, then this C prime will be equal to over r cos of theta. So there will be only the potential energy at point A, that is our initial energy, will be equal to our mgr. And we come to final energy that we are going to calculate at point B. And this final energy at point B will be our kinetic energy as well as the potential energy. So you can say final energy and final energy. First of all, we are going to write for our particle, and its potential energy, and potential energy will be equal to our mg r cos of theta. And the kinetic energy, and for kinetic energy will be equal to, this comes as our half m, and we have our u square plus v square plus 2uv cos of theta. And this is the kinetic energy of particle. These both are of a particle. Now we come to the kinetic energy, and this is for hemisphere. And kinetic energy for hemisphere will be equal to over half m v square. So our final energy will be the summation of the potential energy, kinetic energy of the particle, and kinetic energy of the sphere. And this final energy, let us call this as a EF. So we can say that our, according to conservation, we can write our initial energy is equal to our final energy, which gives us mgr is equal to, we have this as mg r cos of theta plus half m, and this is u square plus v square plus twice uv cos of theta and plus of the hemisphere. And we can combine these two terms, and mgr we can take common, so this comes as mgr 1 minus cos of theta, and let us open the bracket also, so we get this as half m u square plus half m v square okay. So this will be half m v square, and this is also half m, but here is a capital M, therefore we can take half v square common, so it will be m plus small m, and then it will be over plus mu cos of theta. And we substitute value of v, we just calculated it, so we substitute value of v, and so we get this as our mgr 1 minus cos of theta is equal to over half m u square plus, this comes as half m plus capital M, and our v we just calculated is our mu, this is minus cos of theta divided by m plus small m and whole square plus mu cos of theta. Okay, and this is quite easy to solve, there is not much here, so let us sort it out. So left side we are going to keep as it is, so this comes as our half m u square plus it will be coming as m square u square cos square theta and divided by m plus small m plus mu cos of theta. Okay. And one second, 2u cos of theta, yeah, this looks good. And furthermore, we can solve it, and it will be giving us mgr 1 minus cos of theta will be equal to half m u square, and we have m plus small m sin square theta divided by m plus small m. And okay, so now we come to our, so we were at point B, okay, and let me draw it here again. So this is center C, point A, and this is point B, and in the downward direction we are going to have our mg. This angle is theta, so this angle will be also theta, and there will be a normal. So we can divide mg into two components. We are going to get this as mg cos of theta, and this component we are going to get mg sin of theta. Okay, and we know that the loss of contact means this value of normal should be equal to 0. This is the meaning of our loss of the contact. And we can write the radial equation, radial, or we can say normal equation, radial or our normal equation, and because of this centripetal force, we can write our mv square upon r will be equal to our mg cos of theta minus m, and it is going to lose the contact when the value of normal is equal to 0. Therefore, we can write it as our m u square upon r is equal to mg cos of theta. M and m cancels out. Therefore, this gives us that a u square is equal to our gr cos of theta. And next, we are going to substitute this value of u in our already equation which we found out. Therefore, we get our mgr 1 minus cos of theta. This is our half m, and we have our u square, that is gr cos of theta, and this is our m plus small m sin squared theta divided by m plus small m. Okay. And so we can cancel out this mgr. This mgr goes away, and if we solve this 2, we can multiply. So we get this as our 2 1 minus cos of theta, and m plus small m is equal to, this comes as our cos of theta, m plus small m sin square theta. Okay. So this is our the equation which is our required. Okay. And then we have two special cases. One is states that when small m is equal to capital M. Okay. So we have a small m is equal to our capital M. So if we substitute it, we get this as 2 1 minus cos of theta, and this becomes our twice m. And from here on the right side we get cos of theta, m we can take as common, so this becomes 1 plus sin square theta, and our m and m cancels out, so we get this as 4 1 minus cos of theta is equal to cos theta 1 plus, and sin square we can write this as our 1 minus cos square theta. And so let us assume that our cos of theta is equal to our x. So therefore we can write this as our 4 1 minus x is equal to our x 2 minus x square, and this will be nothing but a cubic equation. So we get this over x cube, and this will be over minus 2x, and it will be 4x and minus 4 is equal to 0. Let me check it out. This comes as our 1 second. This will be our 4 minus 4x is equal to 2x minus 2x cube. Okay, so we get this as our 2x cube minus plus 2x minus 4x plus 4 is equal to 0, which gives us 2x cube minus 2x and minus 4 plus 4 is equal to 0. This is the correct one. 1 plus 1 minus, let's got 4 minus x 2x minus sorry, here is the problem, that's why. Now it's look good. 2x x cube minus 2x. 1 second. So we get this as our x cube minus 2x minus 4x plus 4 is equal to 0. So this gives us x cube minus 6x plus 4 is equal to 0. Now it should be correct. Okay, so this is nothing but a cubic equation, and you can just substitute value of our cos, and this gives us cos cube theta minus 6 cos of theta plus 4 is equal to 0. Okay, that was asked in the question, that it will be consisting of a cubic equation. And if we solve this cubic equation, one of the solution will be okay, I think this was asked for only. Yeah. So this is our cubic equation, and so we got two equations. this equation is when m is equal to over capital M, and second equation which we get that 2 1 minus cos of theta m plus small m is equal to cos of theta m plus small m sin square theta, and this equation is when m is not equal to capital M. So these were the two cases as per the question. Next question. It states that, and in this case we have to one second. So it states that a mass m is attached to a massless string of length L. The string is initially wound many times around a thin vertical frictionless pole with the mass touching the pole. The mass is released and the string unwinds smoothly. What angle does the string makes with the vertical pole at the instant it becomes completely unwound? So this question, you can say the final shape, or we can say the final, if you draw the diagram, let me draw the initial one. So initially we have a pole and the string is wound around it. Okay, so it is something like this, and it is having a mass m connected to it, and when it start to loose, the string is going to form it will be something like this. Okay. And the string is completely unwound and its length is given as L. But as it is going to unwound itself with respect to this pole, it is going to form a conical pendulum. Okay, so the final figure is the resemblance of the conical pendulum. Okay, because it is going to wound. Okay, so length is also going to increase, but it's slow and steady. Its radius is also going to increase because the length of the string is going to continuously increase. And finally, it is said that the length of the string is L. So when it is completely unwound, so it will be the shape of this, the string, the figure it will be forming will be a kind of a conical pendulum. And so let us assume that it is making an angle of theta with the vertical, and therefore if T is the tension in the string, so this angle is theta, so we are going to get T cos of theta, and this will go T sin of theta, and our mg will be in the vertically downward. Okay. And so it means that the change in the, we can use the conservation of energy. It means that the change in the potential energy will be equivalent to the gain in the kinetic energy. Okay. So basically we start with the energy conservation. And so we see the vertical drop of the mass from its initial position to the final position. You can see that vertical drop of the mass from initial position to the final position. initial position to final position. And let us suppose this vertical drop is represented as our delta H. Then this delta H will be equal to our L cos of theta. And by this wound, we can just draw it like this actually. Okay, so this is our vertically pole, and this is wound something like this, continuous, like a spring. Okay, as it is going to lose, so it is going to increase its length every time. Okay, it will be forming larger and larger circle. Okay. So therefore, we can say that this is suppose our delta H. So this delta H will be equal to our L cos of theta. Okay, so finally this is our final length. So we are going to get delta H is equal to L cos of theta. And so by energy conservation, we can write that our mg L cos of theta will be equal to our kinetic energy half mv square. Mass and mass cancels out, so we get our v square is equal to 2gl cos of theta. Okay. And now we come to our final position, and final position is nothing but our conical pendulum. Okay. And for that, if r is the radius, then we can say that our r will be equal to L sine of theta. Okay. So r is the radius of the circle. Let me draw it other side. So this is our r. So r will be equal to our L sine of theta. So you can say that our force balance for a conical pendulum, force balance, and this is our conical pendulum. And so we can write that at the final instant, final instant means when the length is completely unwound, that is the length of string is L. So you can say at the final instant, the mass moves in a horizontal circle and whose radius is our r, and that is our L sine of theta. Okay. And we can do a balance, so our t cos of theta will be equal to mg, and similarly horizontal will be our t sine of theta will be giving the necessary the centripetal force. Okay. So we can say our vertical force balance, we can write our t cos of theta is equal to over mg, and our horizontal, or we can say centripetal force balance, horizontal or centripetal force balance, and that will be our t sine of theta will be equal to mv square upon r, mv square upon r, and our r is our L sine of theta. And from here it is quite easy. We are going to eliminate our tension T as well as V. Okay. So we can write from here, we can say that tension T is equal to our mg cos of theta. So we substitute here and we get our mg cos of theta sine of theta, and v we already calculated is our 2gl cos of theta. So we get from here m upon l sine of theta, and this came at 2gl cos of theta, and we can cancel out our L and we cancel out our mg. So from here we get sine of theta upon cos of theta is equal to 2 cos of theta upon sine of theta, and this will be giving us sine square theta and 2 cos square theta, and sine square we can write as 1 minus cos square. Therefore we get this as our 1 minus cos square is equal to 2 cos square theta, and this will be coming as 3 . So we get this as 3 cos square theta is equal to 1, or we can say that our cos of theta is equal to 1 upon square root of 3. Okay. So this was our cos of, or we can say the angle which was supposed to find out. Yeah, so we need to find out the theta. So we get our cos of theta is equal to 1 upon square root of 3. So at this particular moment the spring will be, or we can, the string is completely unwound. And next question, it states that a pendulum of length L is initially held horizontal and released from rest. A nail is located at a distance d below the pivot. When the string becomes vertical, it catches the nail and the bob thereafter moves in a circle of small radius. What is the smallest value of d? Small radius d. Okay, this is d. What is the value of the smallest value of d for which the string remains taut at all the times? So we are having that, you can just draw an approximate figure. Suppose this is our, and here we have a string which is perfectly horizontal, and this is the mass bob and its length is given as L, and just at a vertical below we are having a nail that is located at distance d. Okay, so let us suppose this is the nail and it is located at a distance d. So as soon as, so it is going to come directly here, and this particular moment so this will be our position. Okay. And at is, this string will be caught by this nail, and now this is going to move in a circle, and we know that the total length is our L. Therefore this radius will be equal to L minus d. So it is, the bob is going to move in a circle of radius L minus d. Okay. So you can say that before hitting the nail, the length is our L. but after hitting the nail, the bob moves in a vertical circle of radius. Let us suppose that radius is r, and this r will be equal to L minus d. Okay. And the vertical circle of radius is about the nail. Okay. About the nail. So it means now it is going to rotate about this particular nail. And let us find out what will be the speed. Let us suppose it starts from point A and this is our point B, and this topmost point, let us call this as point C. So we are going to find out the speed just at the bottom B, but before hitting the nail, just before hitting the nail. So you can say the speed at the bottom just before hitting the nail. And let us suppose that speed, we call this as our VB. So we can use our conservation of energy. Okay, so energy at point A is entirely the potential energy, because this height is our height is our L. So this energy will be mgl, and point B is the lowest point. So here entire energy will be the kinetic energy. So you can say that our energy conservation we can write that energy at A will be equal to energy at B. Energy at A is entirely our potential energy, which is our mgl, and energy at B is purely our kinetic energy, that is of half m VB square. So from here we got that our velocity at point B is our 2gl. And now it is going to rotate with a inside a circle. Okay. And this is a nail, and let us call this our N. So we can say that we have a nail N, and this is our radius R. It is going to rotate in a circle from position B and topmost position C. So let us call this height as our delta H. So now we are going to find out the speed at the topmost point, that is our C. Once again we are going to use the conservation of energy. You can say that speed at the top of the small circle, and let us call this speed as our VC. Okay. And we know that our R is equal to our L minus D. So this total height will be nothing but our twice R. Therefore we can say that our delta H will be equal to twice R, which will be equal to twice L minus D. So it means, and so at point B it is only having our kinetic energy, but at point C it is going to have the kinetic energy as well as the potential energy. Kinetic energy is our half mvc square and potential energy will be equal to over mg delta h. So you can see energy conservation. Energy conservation means energy at B should be equal to energy at C, and energy at B is purely kinetic energy, that is a half m Vb square, and energy at C will be our partially kinetic and partially our mg delta h, that is our potential energy. And this mass we can cancel out throughout, and we know that our Vb square is our 2gl, so this comes as our half 2gl is equal to half, and we have this as Vg square plus g twice L minus d, and here 2 and 2 cancels out. Therefore from here we can write, we are interested in this about top speed, that is Vc, so we can say that our Vc square will be equal to, this is about 2g and this will be your 2d minus L. And at point C, so this is our point C, so at point C in the downward direction we are going to have our mg, and there will be tension T also in the downward direction. Okay. Therefore we can say that at point C we can write that our mg plus T will be giving us the required centripetal, that is a mvc square upon r. Okay. And okay, we have to remember that the string will be just taut and that the tension limiting value will be equal to 0. Okay. Ideally it should be greater than equal to 0, but for the limiting value we can consider that value of T is equal to 0. Therefore we can write that for string to be just taut, our tension is equal to 0. So we substitute it here, we get our mg is equal to, and we have our m Vc square, and our r we already know is our L minus d. Mass and mass cancels out. Okay. Therefore we get from here that our Vc square is equal to g times L minus d. Okay. And we have two equations for the velocity at point C, so we can simply equate them. Let us call this as equation number 1 and this is equation number 2. So you can say from equation 1 and 2 we can write that our gl minus d is equal to 2g and this is 2d minus L. So here this g and g cancels out and this comes as our 4d minus 2L. Okay. And which will be giving us 3L is equal to 5d. So we can say that value of d is equal to 3L by 5. Okay. So this is our value of the d, okay, the distance of our nail. That was our value of D, which was the string will be just taut. Okay. So this completes our all the 3 questions for today. And these 3 questions were based on our, you can say, the conservation part, conservation energy, or we can say the conservation of we didn't use anything about the momentum. Okay. And therefore, so this completes the questions for today. Thank you.